All right, so our first younger investigator presenting is Stiven Roytman. He's part of Dr. Bonin's research team. For those of you who have participated in some of our research studies here at the University of Michigan, especially if you had a PET scan, then you were probably part of one of Dr. Bonin's research studies. Steve's involved in web application development, data management, and MRI data analysis, and he'll be talking about the underlying mechanisms of postural instability and gait difficulties in Parkinson's disease. So welcome.
Thank you very much. I am excited to make this presentation happen. So today, my name is Stiven Roytman. I study Parkinson's disease, specifically the advanced symptoms of postural instability and gait difficulties, and that's what we're going to be talking about today. Sorry. All right. So, postural instability and gait disorder or difficulties. They are commonly abbreviated as PIGD, and they're the symptoms that emerge particularly later in the illness. They are the leading cause of falls and mortality in Parkinson's disease, and the existing therapies such as dopaminergic medications and even many of the deep brain stimulation methods are not effective at treating them. So for those reasons, it is important for the field of Parkinson's research to better understand these symptoms and how best to treat them. So to demonstrate the relationship between these systems, what kind of ties them together, I will give an example. So here we have a person without Parkinson's disease and their gait pattern. And as you can see, their gait pattern is steady. When they're standing, when they're not walking, their center of pressure, or rather their center of mass, which is at the person's midline, is right between their feet. So that makes their posture stable. If we compare that to a person with Parkinson's disease, when they're standing, oftentimes individuals with advanced symptoms of Parkinson's have a forward-leaning posture, which destabilizes them in a forward direction as they're standing. So when they initiate gait, the destabilization in their posture causes them to lose balance momentarily and to make an effort at regaining balance by taking a stabilizing step forward. But what we see is in patients with these advanced symptoms of Parkinson's disease, their stabilizing forward step is actually shorter than is needed to stabilize their posture. And because of that, they have to take another step after that, which is also too short to stabilize them. And so as they take these steps, their length decreases, but their frequency increases. And this is a pattern known as festination of gait, as you can see here. And oftentimes, at the end of it, the patient would either fall or have a freezing of gait episode. So that is kind of one example for how posture and gait are interrelated and really can be thought of completely independently of one another. So based on some of our previous work, we have a reason to believe that deficits in sensory processing might be underlying these shared pattern of impairments. So to better appreciate that, we will discuss the importance of sensory processing in gait imbalance and how it might relate to these symptoms. And then lastly, we will discuss some potential non-invasive therapies to improve these symptoms, to better target them. So in order to balance, your brain must know about the state of your body as it's moving and as it's standing. And the only way it can do that is by sensation through your sensory systems. And the first one that usually gets brought up when we're talking about balance is the proprioceptive system, which is, proprioception is the feeling that you experience at your ankles, at your tendons, your muscles as they are being stretched. And what it tells your brain is about the relative position of your body parts to each other and to the environment. So an example of how proprioception contributes to balance will be given here. We first have a person standing in a stable manner on a flat surface. Their center of mass is over their base of support, which makes this posture stable. And there is no stretching happening at the ankle right now. Now, if a person were to sway either backwards or forwards in this position, what it would do is it would move their center of mass away from their base of support, which would make their posture less stable. And at the same time, that would cause a stretching at the ankle, which would tell the brain that the posture is destabilizing and cause a stabilizing muscle response. So, though it is an important system, it is a system that isn't without a fault. For example, when someone is on an uneven surface, when they're on an incline, for example, then the meaning of the stretch at the ankle changes and is no longer as reliable of an indicator of stable posture. So, for example, someone can be standing on an incline and experience a stretching at their ankle, but they would actually still be stable. But if they were to not experience the stretching, they would be unstable. So, proprioception is less reliable on uneven surfaces. The other major factor affecting proprioception as it pertains to balance is neuropathy, which basically is nerve damage. It is damage to the nerves that send the signal from the ankle to the brain. A commonly co-occurring illness with Parkinson's disease is actually type 2 diabetes, which causes peripheral neuropathy. And that has a major impact on the risk of falls in Parkinson's disease population. So 50% of individuals with Parkinson's disease and peripheral neuropathy report having experienced a fall, whereas only 14% of individuals without peripheral neuropathy and Parkinson's disease report experiencing a fall in the past. So is a major contributor to falls. So when the proprioceptive system is no longer a reliable indicator of balance, other systems have to come in and compensate for it. And so the next one that we're going to talk about is the vestibular system, which is located in the inner ear. And it essentially tells you about when you're speeding up or slowing down. So when you hit the gas in a car and you feel that acceleration, that's the vestibular system telling you that. So there's multiple kinds of movements that the vestibular system can pick up on. For example, imagine a person standing, standing, and then they rotate. Now as they rotate, the fluid in their inner ear actually circulates around these canals, and that activates nerve fibers that tell the brain, oh, the head is rotating. And another kind of sensation that the vestibular system allows is for tilt or for acceleration. Like I was saying, when you hit the gas in a sports car and start moving really fast, you feel that with your vestibular system. And also as you tilt backwards and forwards, the vestibular system also feels that. So it is the other form of acceleration that the vestibular system feels is actually gravity, which because of that, there are a lot of quick postural reflexes that are activated by the vestibular system. And it is also vulnerable to the process of aging. So people generally lose vestibular function as they age, which is another risk factor for falls in aging and in Parkinson's disease. And the last one that we're going to talk about, or rather the second last, is the visual system, which we are perhaps most familiar with because it dominates our experience of the world. So the visual system, what it allows you to do is to situate yourself relative to objects in your environment. So as you move around, if you tilt, you will see the whole environment around you tilt, and that tells you that you may be off balance. The other contribution that it has is it allows you to sense the velocity of your body, because as you are moving, the images in your vision move through your peripheral vision, and that tells your brain that you're going forward. So that's another contribution to gait and balance of the visual system. And Now we're going to talk about really the last sensory organ for this talk, and I think the most important one is the brain. So all of these sensory systems that we talked about thus far, the proprioceptive, the visual, and the vestibular, they all come together in the brain. And what the brain does is it combines the information from all three systems to form an internal image of the body's state as it's moving or as it's standing. And so when everything is working correctly, these sensory inputs all agree and form this very crisp, nice representation of the body, which allows the brain to effectively control movements. Now, if something goes wrong with any or all of the sensory systems, or with the brain's ability to integrate that information, what happens is it's unable to form a very crisp representation of the body. The representation becomes blurry and not very precise, which might be the cause of the movement deficits that we see in advanced Parkinson's disease. And so in order to investigate that, we were looking at the ability of people to balance, because that requires integration of multiple sensory systems. So the way we were doing that is we had people with Parkinson's disease either stand on a firm surface with their eyes open, which is like a baseline condition, just being able to stand with most sensory systems intact. Then we had them stand on a firm surface with their eyes closed, which tests the ability of integrating the vestibular and the proprioceptive system for balance. Then we looked at their ability to balance on a foam pad with their eyes open, which looks at the integration of the visual and the vestibular system. And the most important one for this article was the last condition, which involved them standing on a foam pad with their eyes closed. Now, the foam pad makes proprioceptive inputs unreliable because it kind of moves around a lot. And with their eyes closed, they have no access to visual information. So then patients had to use the vestibular system primarily for their balance. And what we found is actually among individuals with Parkinson's disease and freezing of gait, 84.6% of them were unable to balance in that condition. They really had a difficult time. That is as compared to 27.8% of individuals without freezing of gait, but with Parkinson's disease, who had a difficult time on that condition. So what that tells us is there might be a vestibular specific deficit that individuals with Parkinson's disease and freezing of gait have. So the study that I just showed you was using a pretty simple setup with this foam pad, which is really easy to implement in clinical practice, but we needed something a little bit more powered, a little bit more precise to further study this integration of sensory systems. So the setup that we were using was this Neurocom system. And all it is really is just this visual surround with the mountains and the sky and such, and the force platform on the bottom. Now the force platform is actually able to sway forward and backward with the person's sway. So as a person sways forward, the platform would shift as to keep the ankle straight so that there is no stretching at the ankle. And then that way it's able to much better prevent proprioceptive inputs from contributing to balance. And in this study particularly, we were focusing on a subgroup of patients who had postural instability. Now, postural instability had a pretty precise definition, and it was defined as inability to maintain balance when being pulled back by a trained neurologist. So I will play two videos side by side showing one gentleman who was pulled back and was able to retain their balance, so no postural instability, and in the other video, the gentleman is actually unable to retain their balance and they fall backwards, just to give you an idea. Yeah, so the individual on the left, no postural instability. The individual on the right, postural instability. And so what we found is in this subgroup of patients, they had difficulty with maintaining their balance on two conditions. So the most pronounced deficit was, again, on the condition where the proprioceptive input was unavailable and the visual input was also unavailable. 45.2% of individuals with postural instability were actually had a fall on that condition. That is as compared to only 9.1% of individuals without postural instability. And then on the condition with the eyes open, there weren't more falls among individuals with postural instability, but their sway was a lot less controlled. It was a lot more pronounced. So that tells us maybe the story is not that it's all just the vestibular system. There might be something happening with particularly combining these two sensory systems as well that is malfunctioning. And so the latest study that we recently published was looking specifically at freezers, now with this more sophisticated system. And freezers actually particularly differentiated themselves on inability to control their balance on the condition where visual and vestibular inputs were both available. So they had a much more pronounced pattern of sway on that condition than on any of the other ones. And we also found that intake of multiple anticholinergic medications exacerbated that deficit among both freezers and non-freezers, which tells us that the cholinergic system, if it's being inhibited by medications or by other reasons, that might make the balance deficits in Parkinson's disease more pronounced. And so again, we have this piece of evidence pointing to visual vestibular integration deficits. I have a bit of a better kind of presentation here of how the pattern of sway look. So this is sway over time from top to bottom over time. And then we can see on the top row, the non-freezers, they have fairly well-controlled pattern of sway in the forward and backward direction. But then when we look at the freezers, we see these big ballistic trajectories that they have when they're trying to balance with just their visual and vestibular system. So again, pointing to specific difficulty when proprioception is unavailable and visual and vestibular sensory inputs have to be combined for balance. So what I just told you is really fun science and all, but I'm sure you're wondering, how does this relate to the real world? How does it relate to actual situations that a person might encounter? So one potential situation is this. Someone might take a step onto an unexpected incline. So what that does is renders their proprioceptive system unreliable, and thus they have to rely on their vestibular and their visual system for balance. So a person without Parkinson's disease would take a large stabilizing step forward and then have a steady gait pattern thereafter. A person with Parkinson's disease and these advanced symptoms would exhibit that same pattern that I showed you earlier, where their stabilizing step forward would not be large enough to stabilize them. And so they would take another, and they will all get progressively shorter until they either have a freezing episode or they fall. And I will actually show you an individual precisely in that situation in this video. As they take a step on the incline, they will begin the pattern of festinating gait, where they're stepping really quickly, very short steps. And in this case, they will actually fall. So this is a real situation that can happen to a person. So in summary, the evidence is accumulating towards understanding of these postural instability and gait difficulty symptoms as with the impaired sensory processing at least contributing to this deficit. And specifically in conditions when proprioception is unreliable, such as when someone steps on an incline or an uneven terrain, that's when these symptoms are really brought out. And so in light of this understanding, I will now present a few non-invasive therapies that we are either studying currently or will be studying in the near future to address these symptoms. So I want to start with the ones currently under investigation and also kind of the simpler ones. So turn exercise and more systematic version of it, vestibular physical therapy. The basic idea is if you expose your brain enough to this combination of visual and vestibular inputs, it will learn new ways to integrate them to better control balance using them. And then the other one that we're currently investigating is a long name, thermoneuromodulation, Well, all it really is a headset that shoots warm or cold air into the ear. And what it does is it affects the fluid in the inner ear and stimulates the vestibular system. That has an effect beyond just the inner ear, because the vestibular system is connected with many other brain systems. And so the idea is by exciting the vestibular system, you might make it more sensitive in the long run. So these are currently under investigation. And then there are a few more futuristic, maybe experimental therapies that we're looking into right now. So, and I will give one for every sensory system that we've covered thus far. The first one we'll be talking about is the moccasins, which specifically address the proprioceptive system. So what they are is this kind of funky looking boot, and it has sensors inside the boot to detect the various stages of the gait cycle. And it sends a current, it sends a stimulatory current beyond the damaged nerves. So it bypasses the damaged nerves and the neuropathy to allow the signal to make it to the brain, which would enhance proprioception and prevent falls. For the vestibular system, we're looking into adaptive galvanic vestibular stimulation, which is basically an electrode that is placed around where the jaw meets the skull. Oh, sorry. And so they've done sessions with galvanic vestibular stimulation where they send this electrical current to the vestibular organ and stimulate it. And then there is some mixed result in terms of seeing benefits after the sessions, but a lot of the times in the long term, this benefit kind of tapers off. So people have to come in again for a session. So the idea with this system is, instead of having people come in for a treatment session, you have a device that they can wear. And it's strapped with an inertial sensor, which kind of senses movement. And so what it would do is, as a person is experiencing movement, as they're like walking or as they're turning, what it would do is it would send the current precisely at that moment, with the effect being to make the nerves that conduct the vestibular signal more excitable. And so essentially what it would be like is like a volume switch on the vestibular system. So at least with the age-related vestibular declines, that might boost it a little bit further to improve gait and balance. For the visual system, we have this fancy-looking magic leap glasses, which are an augmented reality system. So they have a camera, they can see the environment, and you might be able to detect when a person enters into a situation where they're prone to have a freezing of gait episode, such as when they're walking through a doorway. And what it would do is it would project cues for that person to focus on to hopefully rein in the pattern of gait. So instead of having a fascinating gait pattern, they would have a more adaptive gait pattern. So for example, in this illustration, we're showing like projecting steps onto the floor so that the person may follow them. The idea being that might help prevent freezing of gait episodes. So thus far, we've covered all three of the peripheral sensory organs. But what about the main sensory organ, the brain? So there has been therapies that target specifically the brain in Parkinson's. For example, deep brain stimulation. But that is highly invasive, requires surgery to insert, and for that reason, it is really a last resort option. There have been non-invasive electrical stimulation of the brain with transcranial electrical stimulation, but it is also done on a session-wise basis. So a person comes in and have a specific spot on their head stimulated, and it has the same kind of downside as the galvanic vestibular stimulation, that the benefits tend to taper off over time. So in the same vein as the galvanic adaptive stimulator, the solution might be a wearable system. So a system that both reads brain activity, and when it detects an abnormal pattern, it sends a current at that precise moment instead of at all times or on a session-wise basis. So this kind of headset may look a little bit clunky to wear, but I'm a firm believer that once you know which specific electrodes you should be reading at and the specific electrode that you should be stimulating at, you would be able to trim down the form factor of the device so that you only have the necessary electrodes. And so it would look a little bit more ergonomic perhaps and futuristic looking. and not as burdensome to wear on a daily basis. So there are specific avenues for this kind of device in terms of theoretical uses. So we know there is a specific pattern of brain activity called theta wave activity over the motor cortex, which is at the very top of the head. And it's related to maintaining balance. So individuals with Parkinson's disease who show a pronounced pattern of this theta wave activity have less difficulties with balance, as opposed to those that show a more attenuated pattern. So one solution might be is when you detect postural instability, that a person is swaying a lot with an inertial sensor or some other means, you would apply a current specifically at that time to that part of the brain. And what it would do is it would boost the postural processes and ultimately improve the brain's ability to maintain balance. The other kind of use for this technology is with freezing of gait. So there are known patterns of brain activity associated with the onset of a freezing episode. So I'm a believer that if we're able to detect it before it happens, we should be able to send a current at a precise moment to prevent it from happening, to disrupt that pattern of activity before it blossoms into a freezing episode. And that is all that I had. Thank you very much for participating and for listening to my talk.